In this example, we have a bullet being fired from a gun at 700 meters per second on a platform 8 meters high. And we want to find out the answers, estimate the answers to the various questions using the average velocity table. So we'll start right in by filling out the table. So we've got our time, 0, 1, 2, 3. And we have our velocity in the x, which we are told is 700 meters per second. And it remains constant. The horizontal being constant throughout because there's no horizontal forces acting on it. Then we get a delta x, which is the average velocity times the time. So 700, 0, 0, 700, 1400, and 2100. And then we'll shift colors here to go to the vertical, the z. So we have the vertical z, and that's going to be 0 in the beginning. No time has passed, so there has been no acceleration on the bullet. And so after 1 second, it's minus 10, and 2 minus 20, minus 30. And the average velocity in the z, well, 0 minus 5, minus 10, minus 15. And we have our delta z, which is the average velocity times the time. So 0, minus 5, minus 20, minus 45. And identifying the drop, we're dropping 8 meters. So 8 meters would be between 5 and 20. So we can see this is where it occurs right here. We're looking at an impact a little bit after 1 second. It would be minus 8. The instantaneous velocity vertically will be a little more than 12. The horizontal displacement will be a little more than 700 meters. So how long will it take to hit the ground? We are looking at, we might estimate that to be maybe 1.2 seconds. And there'll be a plus or minus with that, but 1.2. How far will it land from the base? Let's say maybe 800 meters. And vertical and horizontal components. The vertical we said was maybe 12. So VZ might be minus 12, and VX, because it remains 700 meters throughout. And what is the magnitude of the impact velocity? Well, in this particular case, we are looking at about minus 12 vertical and 700 horizontal. So we can see now that we're looking at a hypotenuse that's going to be a little bit more than 700. And we're then looking at an angle that's going to be very, very tiny, a very, very small departure angle. So a squared plus b squared equals c squared. C is the square root of a squared plus b squared. And so that gives us 12 squared plus 700 squared. And so that's 700.1. And using our significant digits, we wouldn't report beyond 700. So the difference in velocity between the horizontal Vx and the impact velocity is negligible. It's less than our margin of uncertainty in the measurement. But it will be more nonetheless. And then when it comes to the angle, we have the tangent of theta, which is 12 over 700. Theta is the inverse tangent of 12 over 700. So theta then less than 1 degree, 0.98 degrees. So that makes perfect sense to us that it would be a very, very small angle as we expected. So that's how we would use the average velocity table to come by these values. Now let me just quickly review the calculations if they're giving you a little bit of difficulty where certain numbers came by, and those will be in the VZ area. So let me change those. Let me go over those. So we have acceleration caused by gravity. Remember, this column comes from V equals AT plus V0. We have the instantaneous velocity changing due to the acceleration caused by gravity, which is minus 10 multiplied by the time. Vertically, the initial velocity is 0, so that term drops out. So we have minus 10 times 1, minus 10 times 2, minus 10 times 3 gives us those numbers. This average velocity comes from V equals V plus V0 over 2, the average of the velocities, which we can use when the acceleration is constant, like in this case. And so the initial velocity is 0, and the final velocity for the first interval, the first second, is minus 10, so that gives us an average of minus 5. And for the next cumulative interval up to 2, the average velocity, minus 20 plus 0, is 20 divided by 2 is minus 10. And in the third interval, we have these two, minus 30 plus 0 divided by 2 is minus 15. And then the delta z is the average velocity times the time, well, the average velocity multiplied by the time. Minus 10 times 2 is minus 20, and minus 15 times 3 is minus 45. So that's just a review of the details of those calculations. So in part 2 about this, we're asked to make estimates and predictions what will happen. So now we have the same situation. He finds the bullet doesn't hit his target. He switches to a different gun that has a muzzle velocity of 800 meters per second. And the bullets are 10% more massive. Well, that would make sense that a more powerful gun might shoot more powerful bigger bullets. What does it have on each of the following questions? And we're looking for increase, decrease, or remain the same, or / no effect. Explain the reasoning for each. Use a formula for physics principle for the starting point of your answers. And we can use diagrams to assist in your explanation. So this is exactly the type of thing that the AP asks us to do. So what effect does the bullet's new mass have on its flight? The new mass has no effect. All objects accelerate at the same rate, irrespective of the mass. G depends only on the distance between the centers of mass of the Earth and the object. Now, of course, we can reference here Brian Cox's video. We could think about Brian Cox's video where we had the bowling ball and the ostrich feather, and the view of the moon with a hammer and a falcon feather. They both hit the ground at the same time. So how long will it take the bullet to hit the ground? It will take the same amount of time. we've already spoken about the mass. And so when it comes to explaining why they hit the ground at the same time, the free fall time is independent of the horizontal velocity. And of course, in this case, the videos we have in mind are Alan and the cart, and we're thinking about Mythbusters with the gun being fired, just like this particular case is independent of the horizontal velocity. How far will it land from the base of the platform? All right, so in this case, we know that the delta x is going to be average velocity times the change in time. And so since the time is going to be the same, the time it takes to hit the ground, the average velocity will increase. And therefore, the horizontal distance will be larger. And so we can explain that in this way. Delta t remains the same. The average velocity increases to 800 meters per second. Therefore, the delta x will increase. Now, of course, I'm highlighting the bullets here. I'm not writing it out in prose, but at least at this level, we're just concerned primarily with getting the reasons down. The vertical and horizontal components of the bullet's velocity. Well, let's see here. The VZ will be the same. Again, because Vx and Vz are independent of each other. Vx will increase to 800 meters per second. Therefore, the impact, we basically explained that. Sorry, we're jumping on to the next one. Impact velocity. What are the vertical and horizontal components of the bullet's velocity? So we've answered that and justified it, and that's actually given. The 800 meters per second is given. As given. The magnitude of the impact velocity will increase. And so we have Vz and Vx. With this resulting velocity, if Vx increases, then V impact will increase. As shown below, as Vx increases, the resultant impact velocity will increase. And that's the hypotenuse. So what will happen to the angle of the impact? So the angle, depending how we're defining it, but whether it's this angle or in this case, we would usually refer to it, talk about it as the departure angle. But in either case, since these two lines are parallel, we have a transversal cutting those. Those are alternate interior angles, so they'd be equal to each other. So whether we define it as the angle raised from the ground or departure angle from the direction it's fired, the angles will be the same. So the angle will decrease, as shown above. The departure angle from horizontal will decrease because the horizontal leg increases in length. So those are our predictions. So again, a typical AP type thing. We have a scenario, we change one of the variables, how are other variables affected with a justification for them. Lastly, we have our analytical solutions.